Okay, so today I'm planning to cover basically three subjects.
The first, we will start with the potential energy of gravity. For gravity, gravitational acceleration, close to the surface of the Earth, and then the equivalence principle.
Which is the basic principle of general theory of relativity. Okay, so before we start, any questions about the things we had done on Tuesday or even before? Now, we will not be studying the general theory of relativity, but we will discuss the basic principles. Any questions? Okay, so let's start with the gravitational potential energy.
Now, when we were discussing
The potential energy for an arbitrary force, we said that we cannot really talk about a conserved potential energy for an arbitrary force, but the force should have some special properties that we call the force should be a conservative force. So the first thing we have to show is that the gravitational force is a conservative force if we want to define some potential energy for gravity. And if you remember the definition of a conservative force, we had said that a force, let's say field, is conservative if you calculate the work done by that force along a path from A to B is independent of the path. If this is satisfied, in that case we said that F is a conservative force, and hence for such a conservative force we can define a potential energy. And if you remember, we had defined the potential energy at the point, let's say P, in terms of the potential energy at a reference point P0. We had to choose a reference point P0, and we have to also choose what the potential energy should be at the point P0
minus F dot dl from the point P0 up to the point P.
Well, this was basically our definition of the potential energy. Now, in fact, this number over here was arbitrary because basically we can only define the potential energy differences. We cannot talk about the absolute value of the potential energy, but only of the differences. So once we fix the value at one point, then we can calculate the value at any other point. Now, another point of confusion is, why do we have this minus sign over there? In the definition of the potential energy, we always define the potential energy with this minus sign. Why is that minus? Yeah, this one is equal to the minus the work that we have done. So what we are at, because of this minus sign, what we are actually doing is, let's just take the example of this mass. So if I am lifting it up, we had said that I am doing some work on this mass, and hence I am transferring some of my energy into this mass. The work that I have done is nothing but the force that I have exerted on this mass integrated over the path from the initial point to the final point. But the force that I have exerted is if I'm not giving it any kinetic energy but just the potential energy, the force that I exert have to be equal to minus the force exerted on this thing by the conservative force. So this minus F is nothing but the force that I am exerting on this mass, this minus F, if I'm lifting it from here to here. And we would like to say that if I am doing work, it is stored in the potential energy. Question? So that's basically why we put the minus sign over here, so that this whole quantity over here is the work that we do if we want to move the mass from its initial configuration to the final configuration with zero kinetic energy. Okay, nobody can read. Now, the first thing we have to prove is that is the gravitational force a conservative force or not? That is the first thing we have to study. Now, instead of showing that gravitational force is conservative, let's look at a general force. Let's assume that we have a force that is in the radial direction. And furthermore, its magnitude depends only on the radial distance. So this is the general expression of a force. The gravitational force also can be written in this form. And we will prove that this force field is conservative. So we will first prove that this is conservative, and whatever the value of this small f is, whatever this function is, this is always conservative, and if this is conservative, and hence gravity, which is a special case of a force field of this form, will also be conservative. Now let's just assume we have this huge mass, the sun or the planet, and we imagine we take a test mass. This is the large M, this is the small M, this is the initial point. Let's say this is point A, and this is point B. And we can take this mass from the point A to point B. We can use such a path, or let's say this path. So we have two paths, but they are chosen arbitrarily. They're nothing special. You can even choose more complicated path. The derivation will not change. So we will be considering these two arbitrarily chosen paths. So if they are the work that the gravitational force does as this small mass goes from here to here along each path is the same, then it's the same for all paths. So that will be the strategy. So let's consider rings around my large mass M, or very thin strips, circular strips. Let's say this, I have a circle here. Here is another circle. Here is another circle. Let's say here is another one. So these are all circles with different radius. And I will also consider radial line segments. So this is a radial line segment. All these angles are 90 degrees. So the reason why we divide it like this is that we will just, instead of considering this smooth path, I will imagine a broken path. Let's say I would start from here, go radially out. No. First go radially out, then on this arc, then again radially out, on this arc, radially outwards, on this arc, then radially inward. This red broken curve is somewhat close to this continuous curve. Well, ideally, eventually we will take the limit that the angle between these radial lines are very small, and the difference in the radius of these circles, concentric circles, is also very small. So this broken curve will have many more steps, and in the limit that we assume that the difference in the radii of these two neighboring circles goes to 0, and this angle between these arcs, it goes to 0, this broken curve will overlap with our continuous path. So at least in that limit, the work done along this broken curve will be equal to the work done along this continuous path. Now we can do the same thing for the other path. We can go along the arc in the radial direction, along the arc, and then in the radial direction. Again, we can imagine that we can take smaller steps. The critical thing is that these steps are either along the arc or in the radial direction. Now, what is the work done along any arc? The work done along some arc, let's say, it is F times delta R. But remember, the force is in the radial direction. But if you are going along the arc, you are moving perpendicular to the radial direction. So if you are moving along this arc, then delta R is perpendicular to R hat. If two vectors are perpendicular, then their scalar product is 0. If delta R is along the arc, it is perpendicular to the radius vector, and hence along any one of these arcs. We are not doing any work along this arc or along this one or along this one. There is no work done, because the force is always perpendicular to the displacement. Now if we compare the radial segments, let us look at this radial segment on the red curve, and let's look at this radial segment along the purple curve. So what can you say about the length of these segments? They're equal, because the length of these segments is the difference in the radii of these two circles. I mean, these orange lines are circles, although they don't look like. They are supposed to be circles. With centers at the point M. So they have the same length. Now furthermore, what can you say about the magnitude of the force in each one? How can you compare the magnitude of the force acting on my mass when it is over here or over here? They are equal because the magnitude of the force depends only on the radial distance. Since it depends only on the radial distance, this point and this point over here, they are at the same radial distance. Since the radial distance is the same, they will feel the same force. Now the work done along these radial segments was F dot delta R. Well, delta R is in the radial direction. The force F is in the radial direction. So this is nothing but F of R times delta R. Now, delta R in this segment and delta R in this segment, they are equal. So the work done along this segment and along this segment, they are equal. The work done along this segment and the work done along this segment, they are also equal. The work done along this segment, let's say if it has one sign, the work done along this segment over here, it has a different sign. So if I just sum the work done along this segment and the work done along this segment, let me just draw one more circle over there. This goes right through the point B. Now the work done along this segment over here and the work done along this segment over here, when we go back to B, they have the equal magnitude, but they are in opposite directions. In one hand, delta R is pointing radially outward. In the other one, delta R is pointing radially inward. Although both the forces, the magnitudes of the forces, they are the same. They are both, let's say, pointing inward. So there is negative work done over here, positive work done over here. The sum is equal to 0. So the only thing left is the work done over this very small segment on the red curve, which is equal to the work done on this very small segment on the purple curve. So you see that the work done along this purple curve is equal to the work done along this red curve. For each segment on this red curve, the work done is either 0 or there is a corresponding segment on the purple curve in which the work done is equal. So whether you go along the red curve or the purple curve, the work done is equal to each other. Now, of course, these are just broken curves, but this is true for any such broken curve. Now we can just divide this path into this broken curve into smaller radial and tangential segments, and this broken curve eventually becomes this continuous curve. And hence, whether you go along this continuous curve or the other continuous curve, the work done will be exactly equal to each other. Okay, questions? Do you agree that the work done along the red curve and the purple curve, they have to be equal or not? Do you agree with me? The ones on the back? Some sign, yes or no? Which one? This one and this one, or this very small one and this very small one? This length and this length over here, they're also equal. This length and this one. No. No, I mean the idea of why I drew this one, this circle, is that I just want a circle that is passing through my point B. But this one, this length over here is not equal to this one, but the critical thing is that this length is equal to this one. Because both of them are equal to the differences in the radii of these two circles. The lengths are equal, the forces are equal, the magnitude of the forces are equal, the direction of the displacement and the angle between the direction of displacement and the direction of the force, they are equal. So the work done along this path and along this segment, they have to be equal. The only difference is that the angle between the force and the displacement differ by 180 degrees. In one of them it is 0, in the other one it is 180. So the work done is opposite. So the work done as we go from this point to this point, and the work done as we go from this point to this point is 0. So this basically proves that the gravitational force, which is a force of this form, is a conservative force. Now the next thing is what is its form? Now the potential energy at the point P minus at the point P0, this we had defined it in this form, dl, from P0 up to P. Let's say this is my mass, large mass. I mean, it doesn't have to be a large mass, but this is one of the masses that is at rest. Let's say this is the other mass. So where would you like to choose your point P0? Between them, forget this point. Okay, where would you like to choose P0? In the surface of this one. Fine. So this is my point P0. So let me just draw it larger. This is P0. And let's say it has a radius R0. And what should be the potential at P0? Ten. It cannot be 10. Why not? P0, but if you just imagine this is a sphere, the P0 is just a point on the surface of this sphere. This one is P0. Here. At a distance R0 from the center. And your friend said that let's choose U of P0 to be 10. And I said that it cannot be 10. Why not? There's no unit. It cannot be 10. What can it be? 10 joules. Okay, that's fine. It's 10 joules. So let's calculate the potential at some arbitrary point. Let's say, let me change my P0 slightly. Let me put P0 over here. The P0 is still on the surface, but it will just make my life easy to draw it on the projector. Now, this is the point P. At some distance, let's say R, from the center. Now we know that this integral, since f is conservative, we already know that this integral is independent of how we go from point P0 to the point P. So whichever way you like, it will be, whichever path you choose, it will be the same. So let's choose a simple one. So let me choose this path. So I will go first radially out and then along this radial curve. Okay, this is my path. You can choose any path that you like. It doesn't matter because we have already shown that the work done as you go from point P0 to P will be independent of which path you choose. So let's say this point is A. So I can just divide this integral into two parts. One, I can start from P0 and then go to the point A. And then I can start from the point A to the point P. Now what is this integral? The result of this one. I'm going from A to P in very small steps. In each step I'm taking each step along this circle whose center is at the center of the mass M. So dl is on the tangent line, whereas f is in the radial direction. So f and dl, they are both perpendicular to each other at every step. So f dot dl at every step is 0, and hence the integral, which is nothing but sum of all those steps, it will be 0. So this part is 0. Let's look at this one. I'm on this line. Let's say that let's take one particular very small step. This very small step, dl. Now this dl has a very small length and it is in the radial direction. It's radially outward. This dl over here is positive. Let's say that this point is at a distance L from the center. So the force acting on my very small mass when it is over here is minus Gn m large M over L squared in the radial direction. Well, I know that the force is in this direction, which is the opposite of the radially outward direction, which is this r hat. L is the distance. Now the L is the change in the distance from the center, the change when I took one more very small step. So I'm taking these very small steps. I start from the point P0. By taking very small steps, I'm moving to A. And at every step, I'm calculating the work done. Now at every step, the work done by this force F is nothing but F dot dl from P0 to A. Now F dot dl is minus Gn m over L squared times dl. The angle between the force and the direction of my very small step is 0, so cosine of 0 is just 1. This dl is, since it's positive, it is also the magnitude of this vector dl. Now, any questions up to here?
Since we find the force we have to be Fr in the r hat direction, to be more general, you could have simply said like minus integral to A F.
True. FL. True. But then we will not be able to integrate it. Now we will integrate this one.
Right, yeah, that would be more general.
Sure.
Why is the force negative?
The force, well, it's the gravitational force. It is always equal to the product of the masses. I have two masses over here. One is over here mixed, and I'm assuming that I'm taking another mass from the point P0 up to the point P. So I basically have two masses. Just like over here, I have this small mass. I'm taking it from the point A to the point B. So that's why I have the Newton's constant, the product of the masses, and the difference between their centers squared.
Why second part of integral is 0, first part is
Well, you see, the main difference between this part and this part is in the direction of dl. In the first part, the force, let's say, that is my large mass, I'm the small mass. So the force is in that direction, and I'm moving in this direction. So the work is doing some negative work on me in the first part. Now in the second part, the force is in that direction, and I'm moving always perpendicular to the force. So this dl is the direction of my step. This is the force. Since all of my steps along this path are perpendicular to the force, this is 0. There is no work done on me by this force. That is the reason why I chose such a path. So it's one, the radial segment, and another, the second segment is an arc on a circle whose center is in this large mass M. So what is this integral? The integral of 1 over L squared is just 1 minus 1 over L.
So these cancel. The integral just is minus Gn m over L. Of course, L starts from when I'm at the point P0. L is just R0, the radius of the sphere. And when I'm at the point, well, this is at the point A, I'm at the same distance as the point P, which is at the distance R. And U of P is equal to U of P0 plus or minus, or plus minus Gn m over R L. L starts from R0 up to R, and this is just U of P0 minus Gn m over R0, or plus minus Gn m over R. This is my potential energy at the point P. Well, your friend wanted to choose this as 10 joules. Well, that's fine. You just put 10 joules over here, and this is the potential energy. The common choice, the most conventional choice, is U of P0 is equal to minus Gn m over R0. So that U at P is minus Gn m over R. So this is the potential energy due to gravity, gravitational attraction between two masses. Now let's also see how this looks like. Let's sketch its shape. This is U as a function of R. Of course, R starts from 0. Now, U of R is equal to minus Gn m over R. Now, when R becomes very small, then this number over here becomes very large, but minus very large. So it's when R is small, the potential energy goes to minus infinity. When R becomes very large, this 1 over R becomes very small. So this is the shape of the potential energy. Now, when we were discussing potential energies, now whenever you put a mass somewhere, the force acting on that object will be always in the direction to minimize the potential energy. That is also what we had said about when we are reading potential energies. So this graph, by just looking at it, you can tell that the gravitational force acting on my masses is such that it will try to minimize R. So because this is the direction in which the potential energy gets smaller as a number, not in magnitude. If we didn't have that minus sign, this would have been the potential energy. This is U of R is equal to Gn . So this is how it would have looked like if we didn't have that minus sign. So you see, if you want to minimize the potential energy, R should increase. So this is a typical potential energy for a force that is pushing objects apart. But we know that gravitational force is always attractive. So this is how it looks like. The minimum of the potential energy is always at smaller separations. So the system always tries to go to smaller separations. That is because of this minus sign over there. We are not putting that minus sign, it just comes out of the calculation, but the meaning of that minus sign is basically that the gravitational force is an attractive force. Now, any questions on this one? And any machine.
Well, let's see, we have the water dams. Water dams are working with gravity. So they generate electric energy from gravity. So we are making machines using gravitational force. Now let's look at another thing. Here we said that we calculate the gravitational potential energy between any two objects. And as long as they are spherical with mass distributed uniformly, this final relation will still hold. So it will also hold for this object just on the surface of the Earth. And we had also said that the gravitational potential energy of this object is just mg times h. So now the problem is, how do we compare these two? On one hand, we know that the gravitational potential energy between, let's say, just assume this is a spherical object, the gravitational potential energy between this one at the height h from the ground is u at p is equal to, let's say, u of p0 plus or minus gn m times 1 over r plus h minus 1 over r. R is the radius of Earth. So if you take this object, it is at the height h from the surface of the Earth, then we had our derivation just tells us that the gravitational potential energy of this object is just u of p0, wherever you put p0, minus gn mm 1 over r plus h minus 1 over r. M, the mass of this one. Large M is the mass of Earth. Small m, mass of the object close to the surface of Earth. So this is one expression for the potential energy, but also beforehand we know that the potential energy of the point P, we had just said it was mgh. Now, of course, in this definition, we had also chosen some point P0, and P0 is at the point h is equal to 0. So we had chosen the potential at the point P0 such that u of h, when h is equal to 0, u is equal to 0. So we have this expression for the potential energy, also this expression for the potential energy. So if you just look at them, they look completely different. So how can we be sure that what we are actually doing is consistent with each other? Now the trick is that, first of all, if h is equal to 0, if you want to compare the potential energies, you have to be sure that you are choosing the same reference point and you are assigning the same value of potential energy to that reference point. This is the reference point we have for this potential energy. When h is equal to 0, the potential has to be equal to 0. If you look at here, when h is equal to 0, this term is 0. What is left is the potential of the point P0. So if we want to compare this one and this one, we have to choose u of P0 to be 0. So this tells me that u of P0 should be equal to 0. Remember, this P0 we had chosen to be on the surface of the sphere, which now is Earth. So now, if that is the case, on one hand we have the potential energy minus 1 over r.
On the other hand, this should be equal to almost at least approximately equal to just mgh. Now let's look at this one. Sure. So this will be equal to Gn h over r times r plus h. And when we are talking about the radial distances over here, r is something like 6,000 kilometers. If r is just 6,000 kilometers and h is, let's say, just 100 meters, compared to 6,000 kilometers, 100 meters is negligible. It will cause an error which is much smaller than we can measure with most of the equipment. So if we just ignore this one, u is equal to Gn m over r squared m times this number times h. So this is the gravitational potential energy as long as h is much less than r. As long as this is satisfied, this will be our potential energy for an object close to the surface of the Earth. And if you just compare these two expressions, you see that G should be equal to m times Gn over r squared. So at least what we were saying when we were discussing the motion of objects close to the surface of the Earth, we are consistent as long as we identify the axle G with this combination over here. Now let's look at one more thing. Okay, when we were discussing the masses of objects, we were saying, if you remember the first few weeks of this semester, we said we were defining the mass of an object compared to the mass of a standard unit, which was in Paris. So we knew by just using Newton's laws, we could relate an unknown mass to the mass in the standard mass. But that's not a practical way of measuring the mass of Earth. So how do we measure the mass of Earth? If you just Google it, you will find some number for the mass of Earth. You have been given that number in your second midterm. So how does one determine the mass of Earth? We know what this G is, 9.8, almost. We know what the radius of Earth is. Just from the geometry of the Earth, we can measure this radius of Earth. If we can measure this Newton's constant, which we can do by using the Cavendish experiment, if we can measure this Newton's constant, we can determine the mass of Earth. So this is actually how you measure it. And in fact, when Cavendish was doing his experiment to measure this Newton's constant, it was usually referred to as measuring the mass of Earth rather than the Newton's constant, because once you determine Newton's constant, you know what the mass of Earth should be. So this is actually the way to determine the mass of Earth. Other planets. Now, how do you determine the mass of other planets? I don't have a simple answer now.
But it's using so let's say we have a galaxy behind this, some other galaxy. So the light from that galaxy then.
I don't think it will work for the planets. For the planets, the mass is too small for that effect. I mean, the effect will be still too small to measure for planets. We can determine their size. Well, we can determine the masses of exoplanets that are huge by measuring how much their star is
vibrating. You see, although we were always saying that the orbits of the planets are just ellipses around the star, that's not actually true. The orbits are they are orbiting around the center of mass. Both the star is moving and the planet is moving. They're both moving along ellipses. But the center of mass, since the star's mass is huge compared to the planets, the center of mass of the system, the planet plus its star, is almost at the center of the star. Not exactly. If the planet is also very huge, then it will deviate significantly from the center. So the star itself will also be going over measurable ellipse. By measuring the size of that ellipse, we can determine the size of and if we know the mass of the star, well, the mass of the star is easier to measure because the mass will be directly related to how much light it emits. If we know the mass of the star, we determine the size of the ellipse that it makes as another huge planet is orbiting around it, then we can determine the mass of the planet. But of course there will be error bars. But for the planets on Earth, I don't really know. The easiest one would be to measure the period of their orbit, of their satellites. Their satellites. You see, we had said that, if you remember Kepler's second law, it says that t squared over r cubed is just a constant. Now let's determine that constant and then you can go for a break. So let's look at circular orbits. This is, let's say, a large mass M. This is a satellite orbiting that large mass M. Let's say it is moving with a speed v. And v is at a radius r, so its speed will be 2 pi r over t. So if we can measure its period, t, we can determine the speed of the satellite. Of course, assuming we know the size of its orbit. So this should be the central force to keep this satellite in orbit. This should be equal to the gravitational attraction between the satellite and the sun or the planet. So let's just cancel these. So mv squared is 2 pi squared r squared over t squared. This is equal to gn m over r. We can also cancel the m's. So r cubed over t squared will be equal to the Newton's constant divided by 2 pi squared times the mass of the planet, mass of the star. So if you want to measure the mass of a planet, you go and look for its satellites. You measure the size of the orbit of the satellite, you measure the period of the satellite. If you know the r, if you know t, then you know this ratio, which is nothing but Newton's constant divided by 2 pi squared, which is a known constant, multiplied by the mass of the planet. So this would be a means of measuring the mass of planets. So basically, in fact, this is basically the same idea. You are measuring v squared over r, which is nothing but the acceleration of the satellite caused by the planet. And if you know that acceleration, you can relate it to the mass of the planet itself. And this is, by the way, also how you can measure the mass of the sun. From the planets. Well, you know, for example, how long it takes for Earth to rotate around the sun. If you can determine the radius of the orbit of the sun, you know Newton's constant, then you can determine the mass of the sun. Other questions?
Where did Newton's constant come from?
We don't know. The short answer. I mean, we don't know why there is a force called gravity. Just like we don't know why there is a force called electromagnetism. The only thing we know is that there is such a force. Well, there are even people who are actually claiming that there is no gravitational force at the fundamental level. And what they say is that the gravitational force just arises like the forces that arise when I hit this table.